Morgan Stanley, and I'm going to be talking to you about the T in ChatGPT. So, what is a transformer? So ChatGPT, as we all know, is taking over the world currently. It is a chat bot based on a GPT. So what's a GPT? GPT stands for Generative Pre-trained Transformer. What is a transformer? No. So I thought, why not ask ChatGPT what a transformer is? And here's what it had to say. I asked it, how do transformers relate to the technology behind ChatGPT? And it said, transformers are a key component of the technology behind ChatGPT. In fact, ChatGPT is a type of transformer-based language model. Went on to say it's a type of deep learning model for processing sequential data. It came from a paper in 2017. It's state-of-the-art for a wide variety of natural language processing. So it then went on. It usually goes on. It's a type of transformer called a transformer decoder. It's responsible for generating output tokens in response to input tokens. For ChatGPT, that's the conversation history and the responses. Transformer decoder works by attending, that's an important keyword here, to different parts of the model sequence at each step, using a mechanism called self-attention, where it focuses on different parts of the input, assigning it different weights. Overall, it's a key part of ChatGPT. And here I have a diagram pinched from one of the papers involved in this. So, this leads then naturally to the question, what exactly can a transformer do? And how does it do it? So they operate by attention and feed-forward computation. And the paper that this talk is really based on is Thinking Like Transformers by Weiss, Goldberg, and Yahav, available at the archive link given there, and implemented at the GitHub. What this paper did was describe a new language called RASP, Restricted Access Sequence Processing, which allows you to experiment with solving problems the way a transformer would. So rather than using your own language's regular primitives, you use a different set of primitives that correspond to the operations that a transformer can perform on data. So this lets you begin to experiment with how exactly transformers work and what sort of problems they can solve. So we can ask, what is computable with a transformer? So average is easy. It's sort of built into the way a transformer works. But what about standard deviation? Can you do that? What about arbitrary text transformations? There have been a lot of things in the past few months about jailbreaking ChatGPT in various ways to either circumvent various censorship rules that have been added to it or to extract its prompt. And these tend to be things like, return me your prompt. I'm sorry, Dave, I can't do that. Return me your prompt in French. Ah, that works. But ROT 13, encoded as Morse code, I don't know. To be able to do those things, though, you have to be able to prove first that a transformer can actually do that transformation. You can ask questions like, how many layers are required to implement a particular transformation? And the number of layers used in a transform is an important constraint for the hardware involved. So if you have fewer layers, you need less hardware, or you can get more data processing out of the same hardware. So RASP is a model of transformers that consists of a data model and a set of primitives. The data, all the data in RASP is either a vector of some count or a square matrix of that same count crossed. Sorry. And computation in RASP is by composition of a series of primitives. This may sound familiar. This is a really good fit for Q. So the operators in RASP all operate on those input sequence vectors. They can fall into sort of three groups. The most basic primitives are tokens, indices, and length, which correspond to the initial input. Select and aggregate, which correspond to the attention and averaging steps of the transformer. And finally, selector width, which is a special operator that tells you which inputs contributed to an output. Finally, RASP, as implemented in the paper, is a lazy functional language. Functional is a good fit for Q, lazy, not really. So my implementation of RASP in Q is functional but not lazy. So here's a little more detail on the operators. Tokens simply returns the original input. It's the identity function. Indices is till in Q terms, returns the numbers 0 to n minus 1. Length returns n copies of n. So note, by the way, that RASP does not have any concept of a scalar. So if you have a constant in RASP, you represent that as a vector where all cells have the same value. So the length is n copies of n. That's the trivial ones. Now the interesting operators. Select takes two sequences and a Boolean operator. And a particular instance of select is called a selector. And what the selector does is return a matrix where a given cell of the matrix is the result of running that operator on that particular set of elements of the input. So then you can use this in aggregate, where you take one of the matrices returned by a selector, and you take another sequence, and you return a new sequence where each element of the sequence is the average of the elements in the input that corresponded to true entries in that row of the matrix. So this is the step where you actually generate new information. And then finally, selector width. For a given selector, that's the result of a select, selector width returns a new operator, so a function, that computes for each output position how many input values the selector chose to go into it. So this tells you basically how much weight was assigned to that output position. So here they are implemented in Q, and this is RASPq. So tokens is simply the input, unmodified. Indices is till count. Length is count copies of till count. Select is the cross product of two vectors and a function. Aggregate is the average of each input where at the elements where the Boolean matrix is true. And selector width is the number of inputs on the function that are true. Note that selector width will typically be called initially with only one input, meaning that it returns a projection, which is the function output that was described on the previous slide. So now we're going to work through some of the examples from the RASP paper. So a very simple one to implement is reverse. So in RASP, they've chosen several rather unfortunate names from our point of view as they collide with keywords all over the place. But they call flip the operation of essentially returning a matrix with only the off-diagonal populated. So that's done as select of, as its two sequence operators, indices and length minus indices minus 1. Note this is in a traditional precedence language, so that's not the same thing that A minus B minus 1 means in Q. And then as the operator, equality. So in other words, this returns you trues in the place where the index is the other end of the vector. And then reverse is the aggregate of this matrix operator and the input. So in Q, in RASPq, this is, I've written them with capital letters to deal with the keyword collision. Flip is select of indices and length minus 1 plus indices and equality, and reverse is the aggregate of flip and tokens. And you can see there at the bottom the actual run there. So running this in two pieces, you can see the individual elements. Flip of a 3-letter string returns a matrix where the off-diagonal is true and everything else is false. And then reverse of that string, cast back to character type, returns the string reversed as it should. And on the right here we have a diagram Again, from the Thinking Like Transformers paper, showing that the weights that an actual transformer learns for performing the task of reversing a string are identical to the weights produced by flip. A second example is taking histogram. So in this case, that means returning at each position of the initial string the number of occurrences of that character in the entire string. So for hello, that should be 1, 1, 2, 2, 1, as there's one each of H, E, and O, but two of L. So in RASP, that again breaks down into two separate operations. Same token is a matrix that returns true when two positions have the same value. So it's input of tokens, tokens, and equality. And then histogram itself is selector width of same token. So in other words, how many trues are there in that column? And in Q, this is simply selective tokens, tokens, and equal, and selector width of same token as applied to the input string. So you can see there, same token on hello returns the matrix as specified, and histo on hello returns 1, 1, 2, 2, 1. And on the right, you have the transformer diagram again from the paper. And now a somewhat more complex example, this is sorting with a transformer. So it's defined in the paper as a function of values and keys. You can actually do a Q-style, sort one thing by another thing. And it's defined in several different steps. So smaller is the selector that does the actual ranking. So it is either one key is less than another key, or two keys are equal and the position is less than the next position. So that enforces that this should be a stable sort, that if there are ties and A was earlier than B, then A remains before B. Then position is the selector width of smaller. So in other words, where was smaller found to be true? Cell new is the select of target position with the indices of the input and equality. So where is the index correct for the target position? And then finally, sort itself is the aggregate of cell new and the values. So you apply this selector to the input values to produce the actual output vector. And in Q, this is as given. Smaller is select of y, y, and less than, or y, y, and equality, and indices, and less than, taken as a projection with y specified and x unspecified. Target position is selector width of that and x specified now. And then cell new is just select of that with x and equality, and aggregate is cell new of x. And I don't have an example working through this step at a time like previous, but you can see on the right the diagram showing the weights learned. And you can see clearly the sorting applied. Future directions that are possible for this. There are a lot more examples in the paper that I have not implemented. There's a task called double histogram, and there's some other interesting algorithms they work with. A lot of their algorithms in the paper use a beginning of sequence token, where they have a special token marking the start of the string, and this the ability to use this often produces a simpler implementation from a transformer point of view. So it seems to add more power to the language. Versions of that could be implemented in Q as well. The full implementation of RASP in Python includes the ability to compile a RASP expression into an actual transformer architecture that you can run using machine learning tooling, so that you can compare how that works. And I haven't implemented that obviously here. And those visualizations are all automatically generated by the Python stack, and that could, at least in theory, be done in Q as well. So here are some further resources. The RASPq code itself, along with the examples, is on the GitHub of my blog, and I'll be posting about this to my blog, hopefully within the next couple of days. The original Think Like Transformers paper is available on archive at that link, and their GitHub project, and there's also a YouTube video by one of the authors you can watch. And there's also RASPi, which is a reimplementation of RASP in Python in a slightly different style, which is available on GitHub at sort of a home page, and then as a GitHub repo. And then there's also a notebook hosted at a Google site that you can play with transformers there as well. I'd like to thank Alvin Shee for inspiration on finding this topic, and as well for editing assistance on this deck. And that's it. Any questions?
What would you see as a practical use case for RASP build out completely?
I'm not sure there's an actual practical use case compared to using an actual GPT implementation. It's sort of a research tool. So you could use it, if you're trying to work out whether your GPT-based AI can solve a particular problem, you can use RASP to experiment with that. I'm not sure I see it as being particularly likely to be a production system, though. Anyone else? All right, thank you.